So let's try question 3, part A. Dimethylethanolamine, which is also known as DMEA, and M equals 89.14. It's a Bronsted base whose conjugate acid DMEAH plus has a pK of 9.22 and a Ka of 6.0 times 10 to the negative 10. Acetic acid, which has an M of 60.05, has a pK of 4.75 and a Ka of 1.8 times 10 to the negative 5. Calculate the Gibbs free energy knot, so delta G knot of reaction at 298 Kelvin for the acid-base reaction DMEA with acetic acid. So the first important step is to write out our equation for acid-base reactions like this. So let's start out with our DMEA. You can just write it as DMEA, it doesn't matter. You don't have to write the whole thing. Plus our acetic acid. And that goes to our conjugate acid, DMEAH plus our CH3COO minus. So our first step in determining delta G naught is we have to find our KEQ. So how do we do that? Well, it's our Ka of our conjugate acid over it's our Ka of our acid over our Ka of our conjugate acid equals KEQ. So what are those numbers exactly? Well, in this case, the conjugate acid KEQ is 9.22. That's our pKa. So it has a Ka of 6.0 times 10 to the negative 10. And our acid Ka is 1.8 times 10 to the negative 5. So our KEQ is equal to 1.8 times 10 to the negative 5 over 6.0 times 10 to the negative 10, which equals 3.0 times 10 to the 4th. So next, how do we go to our delta G naught? Well, we can use this equation. Our delta G naught is equal to our negative RT ln of KEQ. So now we just plug and chug. So just remember your ideal gas constant in this case. So to solve this, delta G naught is equal to negative, remember we're going to use the 8.314 constant, times our temperature, which is 298 Kelvin, times ln of our KEQ, which is ln of 3 times 10 to the 4th. And as a result, we get negative 25.5 kilojoules per mole. And that's our final answer. All right, let's try problem B. A solution consisting of 7.84 grams of acetic acid and 107.17 grams of water is placed in a well-insulated Dewar flask. To this solution is added DMEA in small portions. After each portion of DMEA is added, the solution is stirred and the temperature measured with a digital thermometer. The data obtained are plotted at right. Interesting. The solid line represents the best linear fit to the data with less than 12 grams added DMEA. The dashed line, the average of the data with greater than or equal to 12 grams added of DMEA. Both equations are given on the plot. Calculate delta H naught of reaction for the reaction of DMEA with acetic acid. You may assume that all solutions have the same specific heat capacity as pure water, which makes our life easier. So first step, we have to find our equivalence point, which is where the heat, basically the temperature of solution doesn't rise anymore. We automatically notice it's this position right here, which we can say is about 31.8 degrees Celsius. So what do we do from here? Well, we know that our line of best fit equation is equal to 1.141x plus 19.03. What is x equal to? X itself is the equivalence point. It's this intersection right here. So if we set this up as an equation, 141x plus 19.03, and then we set it equal to our final temperature, we can solve for x. So we get our final answer of 11.23 grams of DMEA. That's our equivalence point. So now where do we go from here? Well, to start finding our delta H naught of reaction, we can use our heat equations, our heat released equations. So in this case, we can use our equation Q equals mc delta T. As I was saying, so we get an equivalence point of 11.23 grams of our DMEA. How do we go further with this? Well, we can use our heat released equation, which is Q equals mc delta T. Now, the good thing is, because this isn't a well-insulated, so we can use Q equals mc delta T. Now, the important thing to remember is not only is our specific heat capacity is about the same as water, which is going to be our 4.184, but also that this was done in a Dewar flask. So that means that Q of reaction is basically the exact same, if not equal to, our negative Q of solution, because there was no heat lost, because it's well insulated. So let's keep going. So let's find the total mass of our solution at the equivalence point. So we understand that we have 7.84 grams of our acetic acid initially, and then we also have 107.17 grams of water. Now, we have our equivalence point amount of DMEA, which is our 11.23 grams. So we get a total mass of 126.24 grams of total solution, basically. Now we can find our change in temperature, which is, so we initially start at 19.03. We can assume this is about 19 degrees, basically. And we end at 31.8 degrees. So our delta T is 31.8 minus 19.03. Let's say that. That's equal to 12.81 degrees Celsius. So now we can use our heat equation, or mc delta T. So Q is going to be equal to our total mass, which is 126.24, times 4.184, which is our specific heat capacity, times our delta T, which is 12.81. And remember, this is in Celsius. If it was in Kelvin, it wouldn't matter. If it was in Fahrenheit, you would have to convert, but in this case, so it's delta T, so they're both in the same degree. Now, if we multiply all this together, and we remember to put the negative sign because we're asking for Q of reaction, we should get negative 6,766 joules as our Q. So we have an exothermic reaction here. So now how do we go to delta H naught of reaction? Well, delta H naught of reaction is nothing but joules per mole, basically. So we have to find the amount of moles at the equivalence point. And remember, at the equivalence point, our moles of our acid equal our moles of base in a titration. So if we know our moles of acid, we know exactly the moles of base, obviously. So we have 7.84 grams of our acetic acid, and the molar mass of acetic acid is 60.05 grams per mole. So this equals 0.131 moles. So now all we have to do is divide. So we have our 6,766 joules, and we divide it by our 0.131 moles, and we get negative 51,600 joules per mole, which is equal to, so that means that delta H naught of reaction which is just joules per mole, is equal to negative 51.6 kilojoules per mole. That's our final answer. Quick note, if you want to ace your next chemistry or science exam, compete at the highest level, or even place first in national chemistry or physics Olympiads, I highly recommend checking out Chempra.academy. Chempra isn't just another study site, it's a training ground. You get carefully designed, world-class practice problems, step-by-step solution breakdowns, and content that actually teaches you how to think through complex STEM problems, not just memorize formulas. Whether you're preparing for Olympiads, AP and college exams, or you just want the best practice questions available anywhere on the planet, Chempra.academy gives you the depth, rigor, and structure serious chem students need to stand out. Alright, let's try part C. So calculate delta S naught of reaction for the reaction of DMEA with acetic acid. So for this, we can use our delta G naught equals delta H naught minus T delta S naught, which means that T delta S naught is equal to delta H naught minus delta G naught, and it means that delta S naught is equal to delta H naught minus delta G naught over T. So now we can just plug in our numbers. So we calculated in the previous problem that delta H naught is equal to, if I can find it, negative 51,600 joules per mole. So let's plug that in. And our delta G naught is equal to, in this case, negative 25.5 kilojoules per mole. So we can turn that into joules per mole, and we're subtracting a negative, so plus 25,500 joules per mole, and we divide it by our temperature, which in this case is going to be at 298 Kelvin, as stated in this previous problem. If I can find the 298 Kelvin. So yeah, it's 298 Kelvin. And once we divide it and we do the math, we get negative 87.6 joules. Sorry, we get negative 87.6 joules per mole Kelvin. And that's our answer for that. All right, let's do problem D. The delta S naught calculated in part C is negative. What features of the reaction of DMEA with acetic acid cause it to have a negative entropy of reaction? Well, let's write out the reaction again. So we have our DMEA plus our acetic acid. And we turn it into our DMEA H plus our acetate anion. So the main thing that we see that's changing is that we're going from neutral compounds to charged compounds. Anytime you have charged compounds in the reaction, in the products, or just charged reactants in general, your states of movement basically are very, very restricted because of the charges. So because of that, our entropy decreases. There's less ways to arrange our charged molecules compared to the ways that the neutral molecules can move. So we can say reaction results in two charged particles from two neutral ones. And we can say, so remember, because charged particles are solvated by water, which means the water actually will surround the charged particles. It's a solvation by water on charged particles. Constraints the number of orientations the charged particles can have. And that's our answer for part D.